the Hamiltonian formulation of classical mechanics gives us an interesting idea, inspires us to talk about something called the phase space. And this is really why I'm introducing this, because in some sense, the phase space is the one that gives you this space of configurations for classical systems, and that's what you need to compute probabilities in statistical mechanics. You essentially will be computing volume in phase space. So a phase space is if I have n particles in, say, 3D, then the phase space is a 6n dimensional space. Okay. So the space consists, its coordinates consist of the generalized coordinates and the generalized momentum. So if I give you a point in phase space, then that defines the boundary conditions or the configuration, the complete configuration of the system at any given point, right? So the evolution of the system is given by a trajectory in phase space, the complete evolution of the system, right? As a function of time. Do you agree?
Yes, please.
Okay. So let's look at some examples of phase space. Suppose that we have a very simple particle in some n-dimensional system. So suppose that there is no potential energy. It's a free particle. Then what will happen is that the momentum will remain constant, right? And the particle, but it'll have some sort of, if the particle is in motion, it'll be some straight line, right? So the trajectories of the particles will be straight lines parallel to the QI axis. Now, one thing you cannot do is that on a phase space, two trajectories cannot intersect. So if I have two trajectories, they must always go like this. You cannot have trajectories intersecting, because what will happen if you intersect is that at the intersection point, it'll be ambiguous where the particle will go after, because does the particle go like this, or does it go like this, right? So this sort of intersections cannot happen. So all trajectories in phase space, they cannot, however complicated they may be, they cannot intersect. So let me give you what the phase space of a simple harmonic oscillator looks like. Actually, let me do it a bit differently, because its momentum can be its position and momentum can be both positive and negative. So depending on the energy, the trajectories of the particle of a simple harmonic oscillator will be given by ellipses. These ellipses would, oops, sorry, that's not an ellipse. Okay, and these ellipses would not intersect with each other. So this is not a perfect ellipse, but right. And why are the ellipses? Sorry, they should be, and the size of the ellipse will be a function of the energy, right? Because as you know, when the particle is going through the origin, its momentum should be its greatest. When the particle is at the extreme point of its oscillation, the momentum would be zero. That's why they're ellipses, right? So does this make sense? Okay, so what if we took a harmonic oscillator and introduced a small damping term so that it's still oscillatory, but it's there's some damping. So in that case, a possible trajectory would be, say, starting here and then going around, trying an ellipse, but it's actually falling short because it's losing energy, so it's just going to spiral inwards. And after some time, yeah, sorry, that's probably not the most accurate. But if I started from a slightly different initial position, then this guy would still do the same thing, but in a way that doesn't intersect the previous trajectory, right? Because something like this, okay? Okay, so that's basically what, my phase space is. So any questions so far?
I had a question about the orientation of the curves that you just drawn.
Yeah.
So, মানে তীর চিহ্নগুলো আর কি ওগুলো রিভার্স করার কথা না উল্টো দিকে
Sorry?
In the first diagram, wouldn't the orientation be reversed, like the yeah, the arrows? Sorry.
Sir, I think it would depend on the initial
Yeah,
condition.
it depends on the initial condition. Yeah, it could be either way.
মানে P হচ্ছে তো ফার্স্ট ডায়াগ্রামে P হচ্ছে নেগেটিভ, সো P যেহেতু মানে যে ডট
Oh, I see what you mean. Yeah. That's a good point. Yeah. So what Mian is saying is that if Q is changing in the positive direction, then P should change in the positive direction as well.
yes.
Yeah. I think I agree with you. Yeah. That's good. Yeah. Awesome. That's very good. Yeah. So if Q is changing in the if Q is increasing, P in that direction should be decreasing, right? So it should be like this. It should be like this, right? Yeah. Okay. Any more questions?
So the second figure changed too, I guess.
Yeah, the second should be, yeah, let's it should be no, that doesn't work, right? Let me see if I can flip this. Okay, let me erase this and redo this. Yeah, unless we call, yeah, that's good. Yeah. So this should be like this. Okay. And there's a lot of damping I put in. Okay. Okay, any more questions? Okay, so I'm going to just remind you to submit the first assignment by Friday, and then I'm going to assign give you another assignment, okay? If you're late by 1 or 2 days, that's fine, but try to do it by end of tomorrow.
Yes, sir.
Okay? Any other questions?